Welcome, everybody. It's a pleasure for you to join our distinguished lecture this week. We have Professor Esteban Jobbágy from Argentina. Before I introduce Esteban, I want to thank the Global Institute for Water Security and the Global Water Futures Project for underwriting this seminar series, now in its 10th year, as I've been noting the last couple of weeks. Don't forget, next week we have Lindsay Nicholson coming to us from the University of Innsbruck in Austria, and she'll be talking about the hydrological impacts of deglaciation in mountain environments. We want to note as well that we're coming to you via Zoom from Treaty 6 territory and homeland of the Métis. And of course, we're paying our respects to our First Nations and Métis ancestors and reaffirming our relationship with them and commitment to understand the hydrology and water resources of these important areas. But it's my great pleasure to welcome a friend and colleague, Esteban Jobbágy. He is a research scientist and adjunct professor in San Luis, Argentina. His main affiliation is CONACYT, and you'll hear a bit about that in his talk. And he's linked, of course, with the National University of San Luis. Esteban has made some quite deep impacts in the field of ecohydrology, uncovering new mechanisms by which land use change and human activities alter ecosystems. We'll hear a bit about that today. And not surprisingly, he's received many accolades for this work. It's a list too long for me to go through completely, but a few of the more important ones within the American Geophysical Union, he's received the Ambassador Award in 2018. He's a fellow of the American Geophysical Union, and more locally is received from the president of Argentina, de Kirchner, the Bernardo Hauso Award for career contributions by a scientist under 45 years old. Esteban is someone that I spent some time with in the months leading up to the COVID pandemic, and had to make a very unexpected and hasty return from my time with him. But the time we were together was really stimulating for me scientifically, and we had really a great time. And it's so good to see him again, and to turn it over to you now, Esteban, for your talk. And thanks so much again for joining us.
Thanks, Jeff. Thanks a lot. This is a great pleasure for me to be here in this series of seminars after so many really distinguished speakers before my humble presentation today. And it's also a pleasure to connect with you again after this weird period that we went through over these years of the pandemic. I will start presenting or sharing my screen.
Looks great.
Well, the first thing I want to say is that what I will be presenting today, and in the same way, the awards that Jeff mentioned are not for me, are not about my own work, but the work of a big team of people in San Luis. San Luis is a small town, medium-sized city in the center of Argentina. Over the last 20 years, we built a nice group working in ecohydrology and the interfaces of the water cycle and land use, agronomy, and conservation as well of ecosystems. So I will be talking about the coupling between plants and the saturated zone. But we will start at a very regional scale, thinking about this, and then slowly move towards smaller scales and discuss mechanisms, not only natural mechanisms, but human mechanisms as well. A good way to start discussing this connection perhaps is to come and see this map that was published almost 10 years ago by our colleague Yin Fan, and I think has a very well-deserved place in the journal Science because it is the first time we see how deep water tables are from the surface at the global level. And this reconstruction of these patterns of water table depth comes from two sources of data. Modeling on one hand, and a very elegant hydrogeological model that represents water fluxes at the global level, but also data, an amazing amount of data points showing how deep water tables are. And there are two interesting things coming from this study. There are many, but two of them are very interesting for me at least. The first one is that this map has little to do with climate and a lot to do with topography. The main driver of water table depth is clearly topography. And what you see there in blue are places where, according to the model, water tables are very, very close to the surface, less than 0.5 meters deep. And they all match with very flat sedimentary plains. The other interesting thing is that when you match the data and the simulations, there's good agreement where the water tables are deeper than 15 meters. And you can see that here in this plot that shows the area fraction that falls for the model and for the data at different depths. But when you get shallower than 15 meters, there's a divergence between the model and the data. And the model is unable to explain the deep water tables that you see when you dig a hole in some of these blue areas. And as often happens with models, mismatches are much better or informative than matches. And I think this mismatch has a lot to do with what we are seeing in the pampas, in the plains of Argentina, in terms of vegetation changes. And I will try to develop this. So the goal of this presentation is to discuss this blue area in South America and the ongoing hydrological changes and their connection with land use changes. I will first discuss what hydrological transition that we see there is about, then propose some vegetation groundwater coupling mechanisms, and then discuss the responses that people have to these transformations at the level of farms and land use, and at a larger level in terms of governance of the water cycle. So what's going on here? The map on the left shows how much of the area gets flooded at least once in history in the continent. The size of the bubbles shows you that, what fraction of the cells that are 0.5 by 0.45 degrees get flooded. But the colors show how much of this flooding happened before the year 2000 and how much of that flooding is new, the fraction of new flooding. And as you can see, there's a core in the plains that is getting flooded more and more often in recent times, after the year 2000. This new flooding is matching quite well the hotspot of agriculture in the continent. Although Brazil has the largest agricultural area in the continent, Argentina has the most dense and intensely cultivated sector of the continent. These plains, which have very fertile soils, include what used to be grasslands in the past, with a subhumid climate and Aeolian Loessic landscape towards the east, and a drier area with originally covered by dry forests, which we call Chaco and Espinal, which has Aeolian and fluvial soils and substrates. What's happening here is that we are seeing the expansion of floods, about 70% more flooded areas as captured by Landsat imagery, this rectangle that I show here, and at the same time, in the same rectangle, an amazing expansion of agriculture. These reddish areas here are about 80% farming and agriculture, and only 20% something else, typically grasslands and pastures. This expansion is in the order of a doubling in 30 years, making this region a key player in the global grain market. If we make a zoom in this area, what we see is that there is a moving progression of flooding that goes from the core of the plains towards the north. The colors in this map show you when we see the first flooding. Light blue means the 80s, then we get to the green in the 90s. And when we get to the 2010s, 2015s, we get to the red color here. So slowly, floods are moving towards north and west and to drier areas. If you make a zoom in there, what you see is that what used to flood only, or landscapes that used to get flooded only in the very low parts of the topo sequence, are now seeing an expansion of floods, and landscapes that never get flooded since the 80s are now starting to show these new spots of flooding. I should tell you that these floods have nothing to do with flash floods, are what I call slow floods, floods that develop slowly and can last for months, in some cases years. When we look at the same region through time, what we see is that the flooded area of that rectangle that I showed before has its fluctuations that are in a way following precipitation fluctuations, which is what you see in the mid panel here. But what you also see is that as time goes on, we are incorporating new cohorts of flooded areas that were never flooded before, the same colors that I show in the map. If we try to link flooding with precipitation with a dynamic transfer function, we see that there is a good relationship, but the parameter that shows you how sensitive are floods to precipitation shows a big gain first in the 80s and then in the 2000s, which is this line here in light blue. In a way, accompanying what we see in terms of the fraction that is being covered by agriculture in the same region. So we see new cohorts of flooded areas and an increased sensitivity of floods to precipitation. When we look at the water tables in the region, I should say that we have very little long-term data. We were able to gather about 438 points for the last 30 years. There's a widespread water table level rise in all those points. And for the few series that are longer, some of them are almost 100 years, we see a big change in water table levels. Big jump, in some places starting in the late 70s, in other places in the 2000s. When you look at the fluctuations and the year-to-year changes in water table levels, with hidden Markov models, you can describe regime changes. Fluctuations start taking a different dynamic. And you can also see that the sensitivity of water table levels to precipitation is changing its intercept and slope. The regressions show a change in slope and intercept. Besides this widespread, I would call to this point ordinary change in hydrology, we see some bizarre manifestations of the hydrological change. There's a screen capture there of a documentary that we call Rio Nuevo, and it's depicting what's happening in the western edge of the plains, in the driest edge of the plains, where the plains start getting more slope close to the first range of mountains. In a very short period, we have seen the development of totally new water courses. They were featured in The Guardian some time ago. This bizarre creature is also teaching us some things about the hydrology. Basically, if you came here 20 years ago, there was nothing different than that just flat, loessic landscape. But over the last 20 years, these gullies start developing, and they actually developing from bottom up, not from the surface. This is a sapping process. So we see collapses of the ground, and currently we have the largest canyon has 60 meters of width, 25 meters of depth, and it's almost 30 kilometers long. Permanent water flowing is brackish water that's about 5% of what we get as rainfall here in this place. When you reconstruct a profile of this landscape, what you see is that the water tables from the 70s to the mid 2010s went up a few meters higher, about 6, 7, in some places 10 meters higher. As a result, we start seeing new wetlands in the landscape. There were never wetlands before. And in some places, these incisions, which are here depicted in brown, that can be as deep as 25 meters, as I said. The way in which these new rivers develop is by starting from a new wetland that in the next step shows a collapse of the ground and a little lake with some intermittent outflow. Then we have the first big event of sapping erosion, which creates the first canyon and the first deposit, and now we have permanent water flow. And that can keep going on with new episodes of sapping, developing larger and larger incisions and rivers. To these days, these new rivers are getting connected in a network that you can see here that makes all its way to an old river that existed for a long time, that is the main outflow of this part of the plains. What's interesting about this process is that it gives us some perspective through time that we never get with historical records. When you look at the walls of this canyon, you see aeolian sediment all the way down to about 6 meters of depth. Only at that depth you start seeing sediment that has marks of fluvial activity. And when that sediment is dated through thermoluminescence, we find that through the whole Holocene, there was no fluvial activity in this landscape. And fluvial activity is actually 28,000 years old. So what I want to say with this is that we are probably seeing a hydrological condition that's quite new in terms of geological times, at least through the Holocene. Why? Well, before we try to explain what's going on, I would like to make a side comment, and it's that it seems that in many plains, many sedimentary plains that are highly cultivated in the world, we are actually having less and less water. This is true for the western plains in the US. This is true for many places in China. This is true for northern India. In those plains, irrigation is accompanying agriculture. And what you see there is a decline in water table levels and aquifers basically shrinking. Our region has almost no irrigation. This is all dryland agriculture, and we see the opposite trend. So what are the groundwater coupling mechanisms that we may think are involved in these transitions? First of all, I would like to go back to the global water table depth map and the mismatch between the model and the data. And would like to suggest as a hypothesis that a hydrogeology alone tells what the model says. But that model is missing some key ecohydrological mechanisms that explain why water tables in these blue zones end being deeper than what the model says. And another work that was led by Jin Fang, in which I had the pleasure to be part of the team, explored a very interesting aspect of ecohydrology, which is how deep roots are. What explains the depth of roots? This has been under discussion for a long time by ecologists, and there were many candidate variables to explain rooting depth: climate, soil type, soil barriers, type of plants, the taxonomy or the phylogeny of plants. But it ends happening that the main explanatory variable of how deep roots are water table depths. Actually, this is a kind of chicken and egg problem. Is that water tables are dictating how deep roots are, or is the other way around, or both things at the same time? My feeling is that it's likely both things at the same time. In these very flat and stagnant landscapes, the push-pull dialogue between roots and water tables may decide where water tables are. And I can show you some field evidence about how plants can change the position of water tables. And this comes from very basic field studies in which we basically core the soils and take advantage of the diversity of situations that you can find in the landscape. For example, on the left, croplands with eucalyptus plantations. In the center, the native forests of the Chaco within a matrix of cultivated land. And on the right, natural grasslands and again, eucalypt plantations. I will make this part of the story short and show you the synthesis of many years of studies and many publications that we have on the difference that you see in terms of water table dynamics when you compare across fences these contrasting vegetation types. And the main summary comes in this figure and shows that when you put all together in the same bag tree plantations, grasslands and pastures, and croplands, the water table levels that you find are quite different. About 7.5 meters on average in plantations and forests. This is both native forests and tree plantations. Native grasslands and planted pastures are about 3 meters deep, and croplands are on average shallower but with more variation. If you run a more careful, statistically more careful comparison of paired sites, what you get is a mean effect of 1.1 meter for forests and plantations compared to croplands, and 1.5 meters for grasslands, pastures compared to croplands. So it seems that this region that is now mainly croplands may have a different water table if it were covered by grasslands or by forests as it was in the past. It's hard to know because we have very little data to reconstruct it. The other way in which we can study this contrast is to use what relics are there today of what we think was the farming in the plains in the past. And there's a big change in this system, and is that in the past we used to have a patchwork of rotating pastures and crops. And these pastures were very deep-rooted pastures of alfalfa. They were gradually replaced by continuous agriculture, which means shallow-rooted crops. But there are still these relics of dairy farms that today still host pastures. So when we compare, on one hand, pure plots of pastures and crops, on the other hand, full systems of dairy farms, which rotate pastures and crops, with full systems of continuous agriculture, which are the grain farms, we see, based on remote sensing, strong differences in transpiration. This is what you see, for example, in the pasture. About 1,075 millimeters per year and a very steady consumption of water throughout the year. Whereas in farms, if you do only one crop per year, you have much less water consumption in the order of 680 millimeters. And if you do double cropping, which is common in the Pampas, in the wet part of the Pampas, you get 100 millimeters more of transpiration, but still much less than what you get with the pastures. If you compare the full production system in dairy farms and grain production systems, you still see a difference that's more than 125 millimeters for transpiration. Taking this data on what you see from the surface, plus what we know about root depth and direct measurements of groundwater consumption through water table fluctuations in pastures and croplands, and including that in a very simple model, this is hydrosimulation. When we ran from the 70s to the 2010s, water table depths in dairy systems and grain systems, we see that in grain systems, the water tables can get close to the surface, whereas in dairy systems, they are always much deeper, and even during the wet periods, they cannot make it to the surface. Well, one of the main good things about these new rivers is that they open unforeseen opportunities to explore the mechanisms of connection between groundwater and ecosystems. And I will call them the mechanisms that drive the competition between plants taking water out from the landscape through transpiration and streams taking the water out as flow, as liquid flow out of the system. And basically, we can think in these planes about 5 mechanisms, 3 for plants and 2 for streams, that help them gain more water from each other, away from each other. From the side of plants, of course, the very basic mechanism is that plants get access to water first and have the first opportunity to use water from the unsaturated zone, taking it away from the possibility of draining and feeding rivers. But in these very flat landscapes, they also have the possibility of using that water again when it reaches the saturated zone. And now we call that mechanism saturated uptake, which can be, as we always see, in riparian areas or in wetlands, but also because of this flat landscape with shallow water tables, distributed all over the landscape. So these are mechanisms 2 and 3. On the other hand, streams, we see them in ecological timescales as something fixed and permanent, but in this weird case of the new rivers, their speed of change is matching the speed of change of ecosystems, and they are showing their own mechanisms to gain water. And there are 2 of them that I want to highlight. One is deepening the incisions, increasing the hydraulic gradients that bring water to the stream, and also covering with sediment the ecosystems that may transpire groundwater. I will just show you evidence about the 2 most interesting mechanisms for me. First of all, mechanism 1, this is perhaps not the most interesting, but I just want to show you that in these landscapes, if you do, for example, electrical resistivity tomographies, you find extremely dry paddock zones under forest with a large salt bulge. That's deposition, atmospheric deposition of salts plus salts from weathering that have been accumulating for thousands of years. And that has been there, staying there, all the way since the sediments arrived to the current time. When you go to agriculture, what you see is that those salts were washed away and the profiles are at field capacity, are wet. So land use is affecting this first mechanism. More interesting than this first mechanism is mechanism number 3, the possibility of plants making a distributed use or consumption of groundwater. And this is what I show you here. You can see here in this image, the new river, and a fence line separating croplands and a relict of forest. When you go to the relict of forest, and you look at the water table depth through 3 years, 3 growing seasons, you see that the water tables go down during the growing season and recover with an asymptotic pattern during the winter season. These are caldentries, a prosopis tree, like a mesquite, that loses its leaves during the winter. When you compare those wells with the wells in the cropland, you see that they try to reach the level of the cropland and again diverge every growing season. All the levels are falling down because this incision is taking away water with a slower pace. In a fractal way, when you make a zoom in this water table level series, you also see diurnal fluctuations in the water tables, in the forest, but not in the cropland. Very clearly in this dry period in January of 2020. When you take out the sensors that measure these levels, sometimes you find the roots of caldentries at 11 meters of depth, consuming water that's quite salty. So the capacity of ecosystems to consume groundwater is way more than what we tend to think. From the perspective of streams, we see the same mechanisms in a sort of a mirror way. when we measure flow along the stream, something that's very, very difficult because they are changing their configuration all the time. But we were able to reconstruct flows since July 17. Actually, we started measuring in 2009, isolated measurements of flow, more continuous measurements all the way from 2017 to 2020. Something that we start seeing, or something that the data is hinting, is that these streams have low flow during the summer, which is the rainy season, and higher flow during the winter, which is the dry season here. And that's quite shocking. That suggests that precipitation is much less important than evapotranspiration dictating flow here. So again, the flow goes down when it rains, but also when evapotranspiration is higher, and goes up when there's no rain at all, but evapotranspiration is low. This is the case for some of the streams of the new rivers. This is in red, there's the deepest stream. It's 25 meters deep, no fluctuations. Very likely, this stream is so deep that plants cannot make their mark or put their signature on the fluxes. Another thing that we see is that as these new streams develop, some die and some new are born. This is an example here. When we start measuring this one, it disappeared by 2016, but new ones appear. This is a process that is known as stream piracy, one stream stealing water from another. Well, so when we are in these flat places, vegetation and water tables are interacting, and they interact in complex ways. And what we do with vegetation really matters. If we have shallow roots, it's not the same as having native vegetation with deep roots. If we have plants that can consume salty water, it would very likely be different than having plants that cannot consume salty water. But 80% of the region is under farming in the more cultivated parts of the pampas. So understanding what farming responses are to water tables is quite important, not only for farming, but for hydrology as well. One thing that happens when you come to these landscapes that have shallow water tables is that in very dry years, in the dry parts of the plains, you see yield maps that farmers can make with their combines when they harvest that are quite shocking in terms of the variation of yields. For example, in this one, you see an 8-fold variation in maize yield. Actually, in this year, this particular paddock was having record maize production, although it was a very dry year. And that happened in intermediate levels. By taking these yield maps that the farmers make and connecting them with water table level maps that we can make by coring and using a digital elevation model to reconstruct the landscape map of water table depths, we're obtaining these functions that suggest that there's a sweet spot of water table depth that's between 1 and 2 meters for maize, where maize is getting all the water it needs from the water table. And when that water table gets deeper than 2.5 meters, you start seeing an exponential decline in yields. But we also see a decline in yields when the water tables are too shallow, except for rice. Most crops in these plains are crops that cannot tolerate waterlogging. And their response to rising water levels from 2 meters upward is to stop transpiration and growth, likely developing a positive feedback in the system. Besides the yield maps and the water table level maps, we can also see this effect when we look at the surface temperature of these paddocks. And we see that as the water tables get closer to the sea surface, the system gets cooler, suggesting higher transpiration. But when it reaches the threshold of 1 meter, it suddenly gets warm again because transpiration is cut. Farmers have been learning about this. Part of our work in our research group was to develop, together with farmers, in what we call today co-production of knowledge, ideas on how to tame this beast that is the water table. we were quite worried about this positive feedback that is a behavioral feedback. That is, a farmer finds that the paddock is getting waterlogged or has a very shallow water table. Decision, you just quit, you run away because you're afraid of losing your crop. And that makes things worse because you cut transpiration. So what if you have a more complex decision tree? And this is just an example developed with farmers in the west of the Pampas, where depending on the positions of the water tables, we decide whether we are going to do maize, which is an expensive crop, or if the water tables are too shallow, we may do something that's cheaper, but that consumes a lot of water, which is a double crop of wheat and soybean. Now, if we decide to do maize, well, we go for more intensive maize with more fertilizer and more seed as the water tables become more secure. Of course, we can do this in the fall just to prepare, and at the right sowing time in spring, we can decide again. I won't go into a lot of detail here, but I just want to show you that by doing these type of things, farmers can improve their business, but that can also affect hydrology. Unfortunately, the Pampas today is mostly run by renters, not by owners. And the renter decision tree that we know and map is more like this. There's water in the surface, just do not rent and quit, and you're not doing anything in that plot. The machine gets stuck at the sowing time, just quit. Doesn't get stuck, sow your late maize that consumes middle amounts of water, and keep going. Of course, there's more things you can do. At the landscape level, there are things that should be considered in these landscapes that are getting more and more flooded. On the top, you can see some exercise we did with our colleague Steve Lohaid, exploring to what extent tree belts that are relics of forest within the agricultural matrix may depress water table levels. And modeling suggests that when you get to a 50-50 distribution of the landscape, forest and cropland, we may have a good control of the water tables. Something that's very difficult to afford for farmers today, but it's something that needs to be explored. In the lower example, in the Pampas, we have this modeling experiment using Mike Shee as a model, in which we created these squares of 9 kilometers of pure pastures of alfalfa. And we can show that, according to the model, this will create a depression of the water tables, not only in the square, but that will propagate towards the periphery, where the sediments are relatively silty. Not so much in the sandy sediments, which is this region to the right. Well, beyond what farmers do for their own benefit and may do for the whole landscape and the benefit of neighbors, what are the governance responses in a landscape that is getting more and more flooded? I have a few things to show. First of all, we ran many surveys with farmers, asking them what would be the ideal water table level for you. And here comes something interesting. It depends very much on who you talk with. In first place, some farmers, the ones that are in higher places, will want water tables that are shallower and benefit them more. Those that are in lower parts will prefer deeper levels so they don't get flooded. But there are also other sectors. For example, dairy farms don't want a lot of water because they have a lot of logistical problems. Not even talk about towns, which are the ones that pay the highest cost for flooding. On the other hand, something interesting is that these floods are introducing opportunities for wildlife preservation or conservation because they stop farming in places that would otherwise get farmed. So the answer is difficult, but we know now that through land use, we have a control on water table levels. Finally, the last thing I want to bring in terms of governance is some of the lessons that the Rio Nuevo taught us. In these days, the majority of us lives in cities, and our connection with the territory is quite weak, and is mediated by the social networks, the media. Very few of us have a presence in the matrix of the territory. And the Rio Nuevo show how that affects the way in which societies react. The first incisions really damage farms and property of the few rural people that live in the area. Argentina has about 95% urban population. Only 5% of the people live in rural areas. And they were asking for solutions, but they were never listened to. And basically, these flooding patterns or these flooding processes create a pattern of spots. And as long as those spots do not connect with the matrix of the urban world, there's no reaction. The New River is a line that comes out from this plain. And when this line intersected the lines of the urban world, which are the roads, we got the first reaction. The next reaction came when this process affected the very point in which urban societies live. In this case, the town of Villa Mercedes. So hydrological processes, like any environmental process taking place in the territory, won't get tackled by the society as long as it doesn't touch our lines connecting the city points or our points directly. Well, when that happened, we saw some reactions, and the land planning system of the whole country, which has the regulation of which forests can get cut and which forests cannot get cut, was reshaped for the Rio Nuevo area, and all the forest that was allowed to get cut and convert to agriculture was passed to the class in which you cannot cut it. That was a reaction that came from governments, but only 20 years after the process started, when it touched the city. Well, that's all. I hope you learn a little bit about these plains. And as I always said, when you go to weird places or places that are not so much explored by our community of scientists, you learn things that you didn't know. And basically, the most important thing, you get observations that don't match what you know for theory. And those are really good opportunities. That's the type of contribution we want to do from this part of the continent. Thanks.
Well, thanks very much, Esteban. That was a really interesting, informative, and enjoyable talk. So thank you so much for that.
Thanks, Jeff.
We are recording in this small room this week, so we don't have an audience to ask questions, but maybe I could just offer a couple of observations, and then maybe ask you one question just to wrap things up here. So I have a colleague, you may know Adam Ward. He's now at Oregon State University, and he says, what is stream flow? It's simply a catastrophic failure of groundwater storage. And I think you know that description so embodies what you're seeing. And yet, you know, we don't think of that in upland humid systems very often, but I think your study just demonstrates that so nicely. And the parallels, as we've discussed before in Argentina, between your area in the Pampas and Saskatchewan are striking. We too have slow floods, but what the slow floods are doing is creating high water in the prairie pothole lakes. And because we don't have loess, meaning highly dispersive soil, we're not getting new drainage basins forming because we don't have the conditions with the soils just basically, you know, dispersing as they wet up. It's more cohesive till. So things are staying in kind of more lake pockets, if you like. So I find those I don't know, comparisons and similarities and differences interesting. But I guess my question gets to one of your observations, which was the sweet spot of water table. I found that interesting, and I'm wondering if it's linked to the height of the capillary fringe above the water table. And then, you know, I would imagine in your material it's pretty high, I'm trying to remember our conversations in that regard, and wondering what effect that might have, and what that might mean for lessons elsewhere. The sweet spot and possible role of capillary fringe. Could you comment on that?
Sure. Thanks for the comments and the question.
Yeah.
Yes, this sweet spot is actually regulated by two things: the physical properties of the sediment or soil, which decide how thick and how conductive the capillary fringe is, but also by roots.
Yeah.
You can have the same exact sediment, and if you have a maize plant that has a root that is 2 meters deep, as opposed to an alfalfa plant that has a root that's 9 meters deep, your sweet spot will change.
Yeah.
The other thing that's quite important is that the sweet spot could go all the way to the surface if you have plants that are waterlogging tolerant, like rice or like many white plants in the plains. So if you let me share the screen, I will show just one slide. And these functions, the function on the top left side of the panel of the slide, shows what we learned from these yield and water table level maps, and basically suggests that we have this exponential increase in water flow, which follows the response of the capillary fringe, increasing its conductivity as you get wetter and wetter parts of the capillary fringe. But then you have this cap, which is the net atmospheric demand. So when you get more water than what you need, you're okay. But at some point, when the water table is too shallow, you start getting waterlogging. And this function, I think, is the key. And this function, we can stretch it or narrow it depending on what type of plants you have. And it can change also if you have salty water. So I think the key is to use this type of conceptual model and link it with the data on what plants are performance is telling you. It can be yield, it can be growth rates in trees, it can be NDVI, different ways to gauge how well plants are doing with different water table depths.
Yeah, that's great. So in some ways, when you think about the case of your part of Argentina and you compare it to those areas you were referring to earlier in India and parts of Western, plains of US, China, you are in a very enviable position in many ways, because so many of those areas, as we hear about at our institute with the work being done by Jay Famiglietti with Grace and others, they are mining groundwater for irrigation. You have this supply. It has some downside, but with understanding of the process and active management, you can maybe manage it in a way that going forward into the future is a very hopeful message, would you say, for farmers in Argentina? What are your thoughts there?
I agree. I think this brings two issues. First of all, we always cry. Farmers cry all the time. They complain. They are the biggest complainers of all sectors.
Well, don't cry for me, Argentina.
Exactly. It's Argentina and farmers. It's a terrible combination for crying. But of course, you cry because in dryland agriculture, you rely on climate. But it's true that we're getting this extra water, which is, we are measuring this. It's making our farming much more stable. The fact that we're having these shallow water tables. So the first question is this bad? Is this good? And the lesson after the last 10 years is that we, in terms of farming, we are gaining a lot more than what we are losing. So we are in a great position in that sense. We have no cost of irrigation. We have no cost of drainage. We are just living with nature as we can.
Yeah.
With that being said, the next question for me, the $1 million question, is why? Why our farming systems are not irrigating as much as the US, China or India are doing. The number one reason I think is that our farming systems are highly taxed as opposed to those farming systems that are highly subsidized. But that can change. The price of soybean and maize can also change. And if those prices change or the equation changes for farmers, I think irrigation will take off. And we should get prepared to learn from the lessons of other places that irrigated too much and get ready to have sustainable irrigation in the near future.
Yeah. Yeah, because, you know, wells for irrigation just go deeper and deeper every year until they can't go any deeper. And there are so many case studies of that, aren't there, in Southern California and in India and elsewhere.
Subsidence, degradation of the water quality, and of course levels going down and down. So, but it's going to happen. I think eventually this is going to happen. We're going to be irrigating more, and we better learn from the mistakes of others. Yes.
Well, maybe on that note, we'll say thank you so much for this talk. I think it was both stimulating in terms of the practical aspects and these connections to real people and real world problems, and yet was highlighting some very basic eco-hydrological processes that you are seeing and understanding with clarity that sometimes is much more difficult to see in a more complex environment. So that is just great. Yeah. All right. Well, great seeing you again, Esteban. Say hi to Maria and all your group. Thanks very much.
Say hi to Beba, and I hope to see you in person soon.
Yes. Bye. Okay. Bye-bye.